Let me scoot it over a little bit. Oop. Try that again. I think I'm one off. There we go. So now I can ask, how close is my correlation matrix to my actual, I can ask how close is the correlation matrix to the actual data. Well, 7235 versus 7151. Let me scooch this up a bit so I can get access to my, there we go. I mean, I'm going to have to zoom out a bit, I think, to be able to see all of this. Okay. 0.035 versus 0.086, that's not too bad. And if I look at these values here, let's see, what's the highest of the values? Looks like it's about 0.6029. Well, look at the model. The model there says, so my actual correlation between item 11 and item 10 is 0.609, but the model only estimates that my correlation should be 0.566. Right, so it's not quite perfect fit in this case. And let's see, what's another one? If I look at the correlation between 16 and 11, it actually turns out that it kind of underestimates the correlation a bit from what it suggests it should be, 0.69 versus 0.71. Now, this is overly precise in the manner in which we'd actually be looking at this, but this is exactly what state is doing when it's, oh, I'm sorry, any SEM program is doing when it's trying to figure out if you have good fit. If I did estat residuals, okay, here are the residuals of the covariance matrix, and it's saying, it's trying to indicate to us which of these, so again, I technically was looking at the difference of correlation matrices, but this SEM, the SEM function in Stata will always give us the covariance, how far off the covariance matrix was. Again, you should always expect to see zeros down in the diagonals because it's easy to make the variances match up. It's the covariances that are a little tricky. Let's see, which is the one that jumps out the highest? I see 0.08. I think higher than 0.08, so 0.08 and 0.083 in magnitude. So Q13 and Q16 are in the 0.08 range, and what was the other one? Q14 and Q11 were in the 0.08 range. Something suggesting that for some reason those look to be the correlations that were the covariances that were the farthest off. And I think, let's see, what were they again? 14 and, so it's 14 and 11. And the other one was 16 and 3. Let's take a look at the correlation matrix. So those were the ones that were the farthest off in the estimation process. So 3 and, well, did I mark the right one? I don't think I did. 3 and 16. So how far was 3 and 16 off by? Well, 0.53 versus 0.56. Okay. What about 11 and 14? So this one's 14, right? And this one's 11. Oh, wow, look at that. So is
15 and 10?
Well, I'm looking at the values that started with the values here. So 16 and 10 is off by 0.03 in the covariance matrix.
Okay.
Yep. Now the problem is interpreting these is tricky because the covariance matrix captures the covariance matrix captures not just the correlation but also the magnitudes that it's estimated. So in this case, it looks like this one looks to be the worst, doesn't it? Look at these values. This estimates 0.52 of a correlation between 11 and 14. And this one estimates it to be 0.59.
They do look to be off by the same magnitude, actually. Yep. So let's do this. Let's check the. Yep. Let's check the differences here, because we're going to see. So we could actually look at each of the. Oops, no, that's too much. All right. So now again, we're not expecting to see anything on the diagonals. Our diagonals are all zeros, which is good, because if you estimate the correlation to be 1, it's not 1. So let's see, which of these are the biggest now? This one, 0.07, 0.07, and it looks like those are the biggest. So this is really curious. So when we look at the covariance matrix, the largest values in the covariance matrix appear to be 3 and 16 and 14 and 11. 14 and 11 is still bad in the correlation, but so is, what was it, 16 and...
I thought it was 16 and 10, but I might be agreeing around 16
I think it's 16 and 3, actually. Yep. Let me copy these down here, and then I'll do it like this to help. Yep. So this one's 16 and 3. Yep. So each approach gives us slightly different information. Now, it turns out we're going to see that there's other tools that we have to look at what's happening here. Okay. So there are other things that can be taken into account as well, and other techniques that we'll use to determine this. It's very rare we'll have to actually go back and look at these matrices, but it's really important to keep it in your back of mind that these are the squares that are being changed. It's the matrices that are in the background. Question?
I think usually when I roll with residuals, I'll do like a leave one out test, like a variance test. I don't know. Is that something you would do in this as well?
Not in this context.
Okay.
Yeah. Yeah. So that's more looking for like issues of multicollinearity and things along those lines. Yeah. Because in this case, to leave any one of your variables or your residuals out, or the covariances out, you're actually changing the numbers of your. In this case, you're drastically reducing your sample size if you want to think about it that way.
Yeah, I would just leave out one subject and all of their data.
To check to see if the what's the purpose for that? To see if
there's an outlier like affecting
yes.
your model.
Yes, definitely.
And if the sample.
Yes.
So
and
you
there's
would omit just a single subject and all of their variables that go with them.
Yep.
And do that for each one and create a residuals graph.
Yes. That is more to that's to look to see if an individual is an outlier in the data set.
I was just thinking that would affect how well your model predicted your subject.
Because it's going to influence your correlation matrix and covariance matrix. Right. Exactly. Yeah. Not quite the same type of calculations that we're doing here with the path models, but still good. That's why you look at the correlation matrix. So the correlation matrix turns out to be much more important for us doing SEM than is apparently obvious when we do regression. It's important when we do regression too. It's just we look at it in a different way because, well, we use the idea of the line moving and the size of the squares changing. All right, I'm going to go back to Stata now, and I'm going to do another SEM. So I'm going to bring back the SEM that we did, and I'm going to add now. I'm going to I believe an individual's attentiveness influences the likelihood that they're sociable. Okay. In other words, if you're more attentive, you're more likely to be sociable. Not an unreasonable expectation. If someone can't hold their attention on anything, they start talking to someone and they move away halfway conversation, it's not very sociable. All right, but I'm technically just doing this because I want to try to run this model. All right, so now the model's going to run, and I'm going to get all my necessary output, all my necessary information. And I should have in here, so I have the structural and the measurement part. Attitude is attentiveness is influencing sociability by 0.6176 as the coefficient. And these are the unstandardized values. So let's do SEM, comma, standardized. And let me draw your attention to two things. One thing, actually. Let me draw your attention to this. Look at the, now this is the standardized path coefficient from attentiveness to socialization. So let me clarify what I'm doing in my model. So I'm changing this model here. Let me copy it so I don't actually lose it. So I'm changing my model. I'm actually getting rid of this and saying, no, what I actually want is, more specifically, I want to say, go away, I can't get it to stay right spot to get it. There we go. I'm saying this. I'm saying it actually turns out that attentiveness directly influences sociability. So I've drawn a straight line between it. Well, I didn't do it in a straight line, I don't know. But now, and it says that if I standardize this, that the path coefficient is 0.7335. Now, standardize a path coefficient essentially equates to doing a partial correlation. In this case, there's only two latent values, so that's just the correlation. Well, notice what happened when we actually ran the model. When I ran the model before, I think I can say standardized. Please say I can do it directly. So here's the standardized covariance between attentiveness and sociability is 0.7335, 106. Let me scroll up a little bit and we can look at the path coefficient, the standardized path, and lo and behold, what is it? It's actually the same value. It actually turns out to be the same value. So what we've done is we've now actually gone from a model that we've gone from a single factor model, used it to reconstruct the matrix that would imply for the structure between the variables, the covariance or the correlation. Then we moved to a two-factor model, but when I originally drew the two-factor model, I put the curved arrow in it, and the curved arrow is just saying that there's some correlation. Don't know what the correlation is. The model that I just ran is saying, well, no, let's let attentiveness actually predict sociability. So I turn that model into it. It turns out that I end up with the exact same correlation matrix with this model, the one where sociability is predicted by attentiveness, as I did when I just allowed them to be correlated. That issue of what we call equivalent models is going to prove to be annoyingly important for us. I think annoying is the best adjective to use for that level of importance. It's going to come back and we're going to see it. We're going to see it again. Okay. Oh, sorry, go ahead.
I'm just wondering how different the math is.
It turns out, see, that's the key. In when we talk about model equivalence, what the part that's equivalent is the implied covariance matrix. So mathematically, they're indistinguishable. So the math is actually exactly the same. That's the key. And in some ways, the structure models and Uric-Skog's fancy equations that he put together to rebuild the matrix, they may look different, but the matrix they produce, the covariance matrix they produce in the end, are actually the exact same matrices.
And other numbers are the same as well, too, right?
In this case, they actually all, I think they all happen to be, the standardized values should all be the same, but the errors may actually be different. The variances may be different because they've been parsed slightly differently. But we could look carefully to see if that's the case. And when we talk about model comparisons and model equivalence in a couple of weeks, we'll go back and revisit that a little more carefully.
Are the standard errors also different?
No, they should be the same too.
Okay.
Yeah, because again, that's one of the things that's built off of the essentially the second derivative of the matrices, and that should be the same also.
Okay.
So when your observation about the math being the same is dead on. It actually is. It just so happens that the only main difference usually is that the variance and the variation that shows up is parsed partialed out into different spots.
Yeah. So like it looks like for the errors are smaller numbers in the second situation, but I don't know if that makes it a better way of doing it.
Nope, because it's technically, because the error, so if we look at the error coming from, so these errors here
Yeah.
compared to these errors here need to be combined with the error that comes from the variance of this value here as well. Because it's actually being influenced by the, error from its model measurement, and then partially by the error that's coming in from
the other lane. Yeah. Okay.
Exactly right.
Is there a way for me, it's just a question of this software to click to the command and direct me back to the result instead of
Just running it again, in all honesty, I think Stata's mindset is, oh, it's there, just rerun it again. Short of scrolling back up to it, I'm not seeing anything directly.
Also, is there a keyboard shortcut to get the prior command? So
like there's an R.
Yeah.
I do it all the time.
Yeah.
There is, and I don't remember what it is.
Okay. Because I keep pressing the up arrow and then realizing I have to go to instead of it. Maybe I just.
My brain is telling me it was something like dot arrow, dot down, or dot left, or dot back, and I'm not. It's not. There is a way to do it. If you Google it, I bet we could probably find it. There is a way to pull it in. I'm not recalling what it is off the top of my head. All right, if it's okay, I'm actually going to stop here for now. And do you have any questions for me at this point?
I think I just need some more big picture
Mm-hmm.
references, but I'm not sure of the best place to get that sort of of one of the books that you told us
The
to
best
get.
book
is there one? Yeah, is there one that based on what we're talking about now, just big picture, thinking about the model, but also thinking about an example.
Yep. They do more specific, and that's where I want to start using more authentic data for some of these, so we can start making these connections.
Because it was nice actually thinking about the what actually are latent variables and the things within them, and
I'm gonna say if you
a
can
little more concrete.
access any of Byrne's books. Now, Byrne is going to describe them in relation to whatever program you get, or each book is about a different program. But she's very good about kind of walking you through the idea behind the models. And I'm pretty certain we have a handful of them here in the library. So you could probably even just go grab a few of them. So it's Barbara Byrne is her name.
That's not one of the ones I asked.
Yeah, they are. The Barbara Byrnes are. I didn't specifically put those on the list because they're specific to everything but Stata. But Stata and R. I'd be shocked if she doesn't come out with anything there soon. I'm gonna turn off the recording here.